Alright, let's continue our discussion with factoring trinomials, and we want to look at some examples that have some slightly larger numbers. I want to show you how we can take care of these guys. Now I know how some of you are, and you just want to put everything into the calculator. Now we could do that, but I'm going to choose not to do that. Okay? I want us to use the talents that we have. Now if I look at this guy, just like we've been doing, you look for the greatest common factor. This guy doesn't have a common factor other than 1, so we know that he should factor as two binomials. X squared is going to break down as x times x, and then you want to multiply to get this positive 90. But how do you multiply to get a positive number and still have negatives? You need two negatives. Now I want to show you two different ways for getting the 90 and getting the 21. One way is to just make your list of factors. That means you're going to have to know how everything breaks down. So 90 can be 1 times 90. 2 goes into 90 45 times. 3 goes into 90 30 times. Now at this point you should still be thinking about how you're going to be able to combine these guys to get a negative 21. Since they're both negative, you know these guys will have to add to give you 21. That's 91, 47, 33. Not yet. Does 4 go into 90? Oh, not evenly. And here's the thing, if 4 doesn't go into 90, 8 won't go into 90, or any other multiple of 4. Does 5 go into 90? 5 goes into 90 18 times. So not quite. Does 6 go into 90? Well, since 2 and 3 both go into 90, that means 6 goes into 90. And 6 goes into 90 15 times. And then your last combination, see 7 doesn't go in. We already said 8 doesn't go in, but then you know that 9 goes in, which is 10 times. So what we do is we go through the list systematically. Don't bounce around. You bounce around, you're going to miss something. We started with 1 and we worked all the way down. We got to 9. It was 9 times 10, so after 9 would come 10. So we'd just be going right back up the list here, so that doesn't help us out. Now, we're looking for that pair that's going to add to give me 21. And it's the 6 times the 15. So, when I look at these guys being negatives, negative 6 and negative 15. So when I check my work, on the inside here, I get negative 6x. On the outside is negative 15x, and there is your negative 21x. Now, I want you to know that this is not the only way we can go about finding these factors. In fact, one way that I really like to do is using a factor tree. So let's look at that. I'm going to take 90 out here on the side, and I'm going to do a factor tree for this guy. Now here's something that we already know about 90. You know that 90 is 9 times 10. And what you're doing with this factor tree is you're going to break this guy down as far as possible. Get it to this prime factorization. 9 breaks down as 3 times 3, and 10 breaks down as 2 times 5. Now this prime factorization here can help us come up with a list of factors over here. You're trying to see, of course you know 1 and 90. But then look, what about 2? Does 2 go into 90? Of course. Here's your factor of 2 right here. If 2 goes in, look at the remaining factors. 3 times 3 times 5. Well, that's 9 times 5, and there's your 45. Does 3 go into 90? 3 goes in right here. Here's your 3, and you'd be left with 3 times 2 times 5. So when you look at 90, that's 3 times 3 times 2 times 5. Well, there's 6 times 5, and that gives you the 30. When you look at the prime factors, can you find 4? In order to have 4, you need to have 2 times 2, but you only have one factor of 2, so you know 4 doesn't go in. What about 5? Here's your 5. 5 goes in with what left over? 3 times 3 times 2. This is 9 times 2, and that's how I got the 18, right there. Well, after 5, we said, what about 6? 6 is right here, is 3 times 2. So 3 times 2 would be these two factors. The other factors would be the 3 times 5. So this is where I got the 6, and this is where I got my 15. Now we said as we went through here that 7 doesn't go into 90. 7 is a prime number, but 7 does not show up here in the prime factorization. Other prime numbers you wouldn't see, you don't see 11, you don't see 13. So we've exhausted all of the possibilities here. So by using the factor tree, you could see 6 times 15, just by kind of rearranging these factors here. You know, that's one way. Now I want you to see another way of doing this. Okay. Let's try another example. We're going to try x squared plus 23x plus 132. Now at first glance this may seem quite frightening to you. The 132, really, Mathman 24, don't you love us? Okay, sure. Does it make you feel better? I didn't think so. Now let's do the factor tree to get an idea about what's going to go on here. Now when I see the number 132, how does this guy break down? Well, I know that since this is an even number that 2 goes in here. And 2 goes into 132 66 times. Well, can 2 go into 66 again? 2 goes into 66 33 times, and then 33 breaks down as 3 times 11. So you can see here that these guys make up your prime factorization of the number 132. So that's going to help us finding those factor pairs that give us 132. Now we know that when we break this guy down, that we expect the x squared to break down as x and x, and then our signs, everything here is positive, so both of my signs here will be positive. Now I've got to get a 23 out of this. Okay, well, let's make a list of factors and see what we know. We've got 1 and 132. That's already pretty excessive. We already saw that we had 2 and 66. Well, does 3 go into 132? Here's the factor of 3 right here. What are you left with? 2 times 2 times 11. 2 times 2 is 4, times 11 is 44. Let's see, I've got to add to get 23, so I'm still a ways off. But I'm not going to jump around. I'm going to go through it piece by piece systematically. You see that 4 goes in, because here's 2 times 2, that's 4. And 4 goes in 3 times 11, 33 times. What about the number 5? Does 5 go in? There's no factor of 5 here, so 5 doesn't. But you see that 6 goes in, because 2 times 3 is 6, and then you've got the remaining factors of 2 times 11 is 22. How about 7? No 7. 8? 2 times 2, I don't have a third factor of 2 to give me 8, so no 8. 3 would require 3 times 3, 9 would require 3 times 3. There's no 10. Then you got 11. How many times does 11 go in here? Here's 11. 2 times 2 times 3 is 12. And finally, when we get to 11 times 12, we see that this is the right combination to fill out this factorization. 11 and 12. Because when we check our work, on the inside we get 11x, on the outside is 12x. So there we go. So we did the prime factorization to give us an idea about what we're going to do here. And then we used the prime factorization to get our list of factors. And we found the correct combination. You know, sometimes this isn't where you want to go. And making the list of factors might be a little bit too much for you. I don't know. So let's try this example. I'm going to show you a slightly different way for working this. We're going to look at having x squared minus 5x minus 104. Well, there are no common factors here other than 1. So I'm going to factor this as a product of binomials. X squared becomes x times x. And then I look at my sign. I need to get a negative 104. To multiply to get a negative, I need 1 positive and 1 negative. Well, now I've got to worry about the 104. How do I break that down? Now you could think about how do you break down the 104, or you could try something else. You know that the larger of these two numbers is going to be negative. We know that guy. But we also need to make sure that the difference of these two numbers is 5. Well, tell you what. Can you tell me two numbers that are off by 5? Well, how about 5 and 10? Because see, if I put a 5 and a 10 here, I would be able to get a negative 5x out. But when I multiply them, I only get 50, not 104. Well, maybe I make the numbers larger. So suppose I do 6 and 11. That gives me 66. I'm getting closer. These guys are off by 5, but I'm still not there. How about 7 and 12? Let's see, 7 times 12 is, well, that's 84. Closer, but not quite. How about 8 times 13? Let's see, if we do 8 times 13, we end up with 104. Alright! Alright. These are the numbers that I need. Now remember, we said the large number has to be negative. So, negative 13 and a positive 8. When I check everything, x times x is x squared. Positive 8 times negative 13 is negative 14. And when I check, the inside is a positive 8x. And the outside is a negative 13x. And there is your negative 5x. So this one was kind of interesting. We didn't do a factor tree. We didn't list all the factors. Instead, we used a little trick here. We know we had to have opposite signs, and the numbers had to be off by 5. So we made a list of numbers that were off by 5, starting with something kind of higher up. Yeah, you could have done 1 times 6, but you would have been far off from that. So 5 times 10, and we were able to increment that, and we got to 104. So there we go. So sometimes a slightly non-traditional way of looking at it can be very useful to us.